Hello, everyone. I'm Ed Verhamme, a project engineer at Limnotech, and I just wanted to review the presentation that I gave at the Coastal Wetland Symposium. Uh, this presentation is going to review what I call wireless wetlands, and you can see my coworker, Greg Cutrell, in the background here. And there's a lot happening with wetland systems. As a environmental engineer, um, I'm always interested in how much water is moving through wetland systems, how we think about them as these transient bodies that are ever changing. And I think we tend to focus more on the biological monitoring of wetland systems. And I wanted to talk about technology. How is technology helping us monitor wetlands? What tools are available today for relatively low cost? So thanks for watching here. Oops, next slide. When we think about how do we set up an observing system for wetlands, I generally approach it with these components that you see on this slide. So if you imagine on the far left-hand side of this slide is our wetland system. So this is our environmental phenomenon. What are we trying to monitor, understand? And usually with sensors, we more start with the simpler hydrology-based ones, how much water is moving. We can also get into water quality, how turbid is the water, how green is the water. There's a few sensors. We can look at soil conditions. We're not monitoring biological beings here with sensors. I think that's a given. There are some interesting telemetry tracking things we can do. We can also, when we monitor chlorophyll, that's going to be a proxy for plankton or living things in the water. So once we understand that phenomenon, we're going to just start walking through this suite of technologies, really. And it's, how to measure the phenomenon, how to save that data, how are we transmitting that data, what is all those things on the left, what are they attached to? Are we sitting on a post on a stream? Are we on a bridge? Are we on a buoy out in the water? As we get to the right of this slide, we start thinking about data management a little bit more explicitly, about data processing. Where is the data going after it's transmitted to the quote internet? And how are people starting to interact and view that data? So there's a lot of different tools available to us. And we can imagine on the far right-hand side of this slide is an actual person. So that person could be a wetland scientist that's sitting in their office, I'd say, watching this system from afar. So they could be watching for high flow events. When should they go and sample? How wet has the system been? And those really help kind of drive some of the, I'd say, pre-visit conditions of the site. This data system might also be used by water managers that are, we're trying to understand phenomenon across a large region or multiple wetland sites. We can use these data systems to, again, aggregate data from many sites and also to draw in other sources of data. So if there's weather stations operated by others that are outside of our ownership, the National Weather Service, for example, we could draw in data into this data system and it would still be a decision tool. So these are the components that I like to think about in terms of setting up how are we using sensors and how is that leading to some decision support system. And they can be cheap. They can cost $50. We can have a $50 sensor that includes the data logger, the telemetry. The platform might be a $5 pole we're going to drive into the stream bank, and the data systems and user interface here. These can get as cheap as even like $1 a month. So we could be talking about very low cost sensors. And I also wanted to help folks think about that phenomenon versus how much it costs to monitor that phenomenon. So if we're always trying to assume sensors are expensive and we're going to only install maybe one or two, but if the phenomenon, let's just say harmful algal blooms, we know it's going to cover 100 square miles. It'd be great if we could have 100 sensors out, really monitoring that boundary or perimeter of it. Or in a wetland system, we want to see how much water is infiltrating, and we know we're not quite clear on that definition of where the cold water is coming into our system. So I like scientists to start thinking about how do we have more lower cost sensors available to monitor these environmental systems. When we look at a wetland system, I just dropped some red dots here on where I think we're typically looking at understanding inflows, outflows, and conditions within a wetland. So I think we have our ideal wetland system in the middle. We have water coming in some way. So whether it's surface runoff, and typically there's an outlet for wetlands, and sometimes that outlet is going to flow to a stream. So these are opportunities for us to install sensors to understand, again, how much groundwater may be interacting with the site. We can monitor water level in small wells drilled into the bank of the wetland. So these are typically also points where people would be going out to collect macroinvertebrate surveys or other data, whether it's looking for the presence of, how wet is the system, how deep is the water. So I also want to highlight the opportunity to cross-train biologists with how to maintain sensors as well. So that the most expensive part of environmental sensing and monitoring is actually the labor to go out and maintain that sensor. So if we're already sending biologists into the field to collect macroinvertebrate data, can they help keep the sensor clean? Can they just make sure that the measurement that it's taking is valid and give that eyes on the sensor? I did want to address sort of one issue I've seen with environmental sensing, and that's whether we're going to be sending data in real time or we're logging locally. I think people usually assume that self-logging sensors are cheaper. We can deploy these. There is an element of how sensors are powered and how that radio might transmit environmental data. There's just so many options available today for how we package sensors with a data logger on board. And by the time you do that, we could add a $5 radio to the, I'd say a self-logging sensor that could transmit over a low-cost wireless network. The reasons to send data in real time, I think, I wanted to talk about some of the maintenance part of it and also the environmental phenomenon. So once you're transmitting data from your wetland system in real time, you're able to respond in real time to the conditions that are changing. So if your sampling program wants you to target wet events, how do you actually know there's water at the site? How do you actually know that your system is behaving as your hypothesis had stated? So I think we're used to we have a hypothesis or a monitoring program, and we're going to have an annual iteration of that. We're going to download data, put it in Excel, process it. If we're transmitting that data in real time, we can really start to do that hypothesis testing and data processing in real time. So we can shorten the lag. We can sort of compress our ability to generate a report or to synthesize data for multiple sites. So I think it helps get the data scientists involved a lot sooner in the project and helps get feedback on how the system is operating and whether we need to either move sensors or change our hypothesis or visit the site again. So the cost barriers are virtually gone for real time. I'm going to show some options here. So it's not so much a cost issue anymore as much as what does delivering data in real time mean for your project, for your monitoring program? And if there's any amount of value in transmitting in real time, there's technology available to do that today. This is what a real-time dashboard looks like. This is actually the Defiance water treatment plant monitoring station. I chose this one because we're monitoring online nutrients. Actually, we have a nutrient analyzer on site that's processing a phosphate and nitrate sample every hour. We're also monitoring basic water quality conditions at this site. There's another page here I'm not showing that's showing water level. So we can just start to get a heads up dashboard of water quality conditions. We can see diurnal oxygen changes. We can see phytoplankton changes, water temperature, turbidity spikes. So this is on the Maumee River. Again, I think the power of this is really evident once you sort of instrument your site. You can just really start to feel what's happening with it in real time. And when you're doing visits to look at macroinvertebrate surveys, you can kind of have this history of conditions in mind when you're visiting that site. So we've had 4 wet weather events, turbidity was really high. So I think this really helps kind of demystify some of the environmental data interactions with wetland systems. Talking about the telemetry a little bit more, I wanted to highlight this new class of telemetry or data transmission that's called low power wide area network. Lpwan, as it's called, it's really a family of technologies that are generally frequency specific, and they're a little bit, they are proprietary, I'd say, in that there's a vendor that makes the communication, what's the actual standard of how data is sent, but the relationship with the vendor to the equipment, these are very low cost radios. This LoRa radio that we use here is less than $5 manufactured. So I think it's more about how you get mass quantities of these out in all kinds of devices. Cell modems, on the other hand, they certainly start out at maybe 10 times that cost, so about $50 a modem. And this graph here is showing kind of these trade-offs between speed, power, and how far we can transmit that environmental data packet. So I think this LPWAN space is going to be lower speed. We're just talking small amounts of data. But we're also using very little amounts of power. It's hard to convey the power saving ability of these new class of radios. They use about 1/10 or even 1/20th the power to send a data packet out as a traditional cell modem, and they can send it 10 times further. And I didn't, there's all kinds of things to talk about with this slide. Satellite, there's a ton of new technologies that are, I'd say, satellite based. So LPWAN is generally a terrestrial base, meaning we have gateways located on land that are aggregating data. If we look at this LoRaWAN network specifically, LoRa stands for long range wide area network. So it's a particular implementation of this low power technology that sits in the 900 megahertz spectrum. And we have, just imagine we have hundreds of sensors deployed within a local area. Some are measuring water level, temperature, soil moisture, and each one of those contains that tiny $5 radio. So every time we want to take a measurement here, this instrument is sampling soil moisture. There's a tiny processor on board that takes a soil moisture measurement, formats that basically into sensor Morse code, and it just transmits that to a nearby gateway. This is a picture of one of the gateways that we use. We can have hundreds and hundreds of sensors all within a listening area of one gateway, and that gateway has a cell modem built into it. So it's just, consider it like a relay device. So if it picks up a sensor data packet, it's just going to relay that to the internet, and then that's going to be passed on to a data dashboard. So this technology, it's kind of like Wi-Fi in that it's providing connectivity to a bunch of devices, but it uses significantly less power and it goes a significantly longer distance. So if we imagine this wetland system again, um, how to, if we want to monitor all these points, we want to see what's happening with the stream, how much water is going in, how much water is going out. We can just place one gateway that's going to cover the site. To give an example, a gateway antenna that's 30 feet off of the ground will receive data from sensors that are located up to 5 miles away. So we can cover a pretty large area with one gateway. And these gateways are just a few $100s, or even less. If you have an indoor building, you can just plug one in. And there's one cell modem account with that gateway. So this is kind of the wireless wetlands concept here, where we're interested in monitoring conditions within the wetland. We like to be able to see that data on a dashboard. We're looking for lower cost sensors to help see this signal and to really help interpret the hydrologic and water quality conditions at the site that we can use to interpret biological data. I did want to talk about, like, why is this wireless concept important? When we shift over to a monitoring program, I wanted to point out the H2 Ohio Wetland Monitoring Program, for example. They're monitoring, are going to be monitoring, it's like 50 plus wetland sites for 10 years. They have to understand how restoration activities are really impacting these restoration sites. So has restoration been successful? What do these sites look like after 1 to 5, 10 years? And a lot of those restoration activities disrupt the hydrology. So we're looking at some inflow change, outflow change, how long water stays in the site, what happens to water in the site. We're generally interested in water quality outcomes. So kind of that wetlands as a treatment is really important for this program. And we've worked with this LEARN group out of Ohio State University, which includes a whole host of academic partners, Ohio DNR. And it's a challenge. I think researchers had an idea of what they'd like to monitor. And then there's sort of the rubric that against what sensors are available, how much do those cost, what's the budget, how many sites can we go to? So, this past year, we've really helped this program apply this wireless wetlands concept, think about what locations you can monitor, trade-offs in cost. And I'm just going to show a little bit of detail of that here. So this is one of the wetland sites called Turtle Creek. And what you just have to do is just sit down and look at all the ways water's coming in and out of the site. What's the largest open water areas that we can monitor? And then we just started going through what sensors are available, how many locations can we put the same sensors, can we measure water level at all of the sites? Most people, when we're developing these wetland sites, have there's a gauge that lets water in and out. These gates, manual gates, some of them are crank driven, some of them are stop logs. We can buy very cheap sensors that monitor the position of either stop logs or the height of the gate. So like just a simple, it's called a pull rope displacement sensor. So we could tie that to, say, the bottom of the gate and fix that to a location, and we can measure that. So I think, we're really interested in how we can interact with passive parts of the project, like these gates that are changed very periodically, and how can we kind of transmit that data. Sometimes there's volunteers that are out moving these gates, or landowners. So you can kind of see there's a whole host of technology that we've chosen and worked with the Ohio State University researchers on choosing sensors. And it's, this is a capacity building project. So I think we've been training some of the wetland scientists and technicians on how to acquire and buy this technology. It's a difficult problem here. There's a lot of interest in this sort of complete understanding of how the site operates, and then is that like, is this a sustainable monitoring program? How much does this cost? How does this scale across the 50 other sites? So I think that's what this group is learning with this project, and we've been happy to help with some of the just pure technology pieces to this. You also have to consider cost. So from that last slide, we transition to this matrix of, well, how much does each sensor cost? What are all the little pieces, cables, antennas that we need here, so we can kind of see the sensor summary on the left, some of the equipment summary on the right. And it's difficult, you can't quite say that, what would the sensor suite look like if we're doing non-real time. I think we can calculate, it would certainly be cheaper, but it's hard to gauge that value of that real-time data. This program, it is a 10-year monitoring program, but if you get yours, if you don't monitor it right in year one, it's not till year maybe 2 or 3 that you understand you've missed some locations. You don't quite understand this phenomenon. You've not sampled. When you were out sampling, you were missing some really key events that came through this system. So it's really hard to quantify getting self-logging instruments in the wrong location and having I'd say a not ideal monitoring program. So I've been really happy with our trade-offs between how we get as many sensors real time as we can, and how we really think about that decision support tool, which is going to be an online website where you can download and interact with all of this data from this wetland site. Just a real quick look at the value of this low cost sensor system. This is a comparison that we have with it's a $5,000 USGS. This is a radar based water level sensor in blue that's owned by the USGS at Old Woman Creek. And we can sort of see the comparison to a $60 sensor, which is the red dots here. So we have a $5,000 water level sensor versus a $60 ultrasonic based water level sensor. So, these are some of the accuracy versus cost trade-offs. There is a statistical difference here between the cheap sensor and the expensive sensor. But, is it worth the $5,000 versus $60 cost? So those are some of the trade-offs we were making when we were going through this spreadsheet. There's some cool sensors out. One is soil moisture. This shows a soil moisture spike that you drive into the ground, and it has internal sensors that can measure soil moisture at various levels within this spike at 6, 12, 18, and 24 inches. So we can start to see how soil moisture dissipates with depth, or how events, when it rains, we see a big spike event in the rain, and we can see that how that propagates down and how it attenuates over time. So a lot of really interesting sensors available. I didn't want to underestimate the value of the relationships between the organizations that are collecting the data and how they share data together. This is stepping back to a different program in Ohio. This is the Smart Lake Erie Watershed program that's being managed by the Cleveland Water Alliance. So this sort of steps to a state level use of sensors, and how a lot of different organizations are measuring different components of this ecosystem, whether it's wetlands, Lake Erie itself, or the shoreline environment, and how they share data. So this kind of gets into the data management system, and I wanted to highlight that the relationships between organizations are always more important than the data they're exchanging. So that decision support system. Just taking a real quick look at some of these sensor packages that we've been putting together. These are ones that are going to be deployed at that H2 Ohio wetland site. We have the soil moisture spike that I talked about. We have the rainfall sensor on top here. We can get a real-time idea of rainfall without the maintenance of a tipping bucket rain gauge. We have solar radiation. We have air temperature, relative humidity, and water level. Another package we put together is our water quality sensors. So this would go in the stream or open water portions, measuring oxygen, turbidity, temperature, pH, ORP, and chlorophyll. So again, there's sort of some, these are lower cost optical sensors that are available on the market today. And we've paired it with a data logger, open source Arduino based system. This is a $60 data logger paired with this is a $15 LoRaWAN radio that can transmit that data in real time. So just kind of thinking about that matrix again. We are working on a large scale implementation of this LoRaWAN telemetry network. So we're trying to cover as many of these H2 Ohio wetland sites as we can. This is a state level effort to fund the LoRaWAN gateways and implementations in Northern Ohio. We also have the ability to do online nutrients. I talked a little bit about the online nutrient center. This sensor at Defiance, this is just a quick look at that, what an online nutrient sensor looks like. We can draw water from the Maumee River and process a nutrient sample on board and transmit that data via an open source Raspberry Pi device to the internet. And real time again, this is showing that online real time nutrient sensor. This time the data is from Old Women Creek. So the orange dots are from the real time nutrient sensor. So we can see the slug of nutrients coming down the Old Women Creek in real time. The ISCO grab samples that we see here in blue really help show that the instrument is producing valid real-time data. But this ISCO data is going to not hit the internet for like 6 months. So it takes about several months before collecting the sample, processing it, and getting it online. Just to look at some other sensors that we're developing here. This is an oil and water sensor that's commercially available that we can pair again with a solar powered radio setup. We're also doing more batch builds. So a lot of the sensors that I showed, once we figure out what we want, we can build a whole bunch of those. So we can build a batch of these, we can lower the cost, we can train students to build and wire and connect these. This is showing our weather station that we're working on, a coastal shoreline weather station, as well as some water quality buoys that we're putting out in Lake Erie. So there's a whole host of technology available. And that's my talk. Thanks for bearing with me as I just went through a whole bunch of different concepts. It's really about how technology gets applied to environmental monitoring, how we think about the field biologist and start arming them with more tools, more devices, and how we help push them towards being part of a decision support system that can operate in near real time. So hopefully you enjoyed the talk, and my email address and phone number is up there as well. Thanks. Bye.